Good evening, everyone. My name still remains the same, Professor Lainka Jani, your facilitator for this course. This is CHM203 class, and we are supposed to be meeting 1 hour every week by 7 to 8 p.m. The link for the Zoom live class has been sent to us. And the first topic for the first week is what we are going to be looking at today. I've sent you the video of this class, and I've also sent you the PowerPoint that cover the course contents. The expectation is that the student are to watch that 1 hour video before the live class, so that whatsoever is not clear about the explanation there is what we can bring to class, so that in the live class, we can use it to solve so many problems, so that you are not afraid by the time exam is coming. You are not afraid to face any exam or any question. So please, let's do due diligence every week to make sure that once in a week, when I drop that video, just watch that through that YouTube link to know what is there. And after that, then you can come to the live class to ask questions on the area that you need more explanation. So I'll be sharing my slide now. Can you see the slide?
Yes, sir.
Yes,
Very
sir.
good. Thank you very much. So let me just start by asking this question. In that topic one that you watched through that YouTube, which is what we are looking at today, is there any area of concerns that you want us to explain better so that we can together solve it in class now? So that it is not the same explanation that we did in the video that we are now repeating again today. It will not be to your maximum advantage. But if you have watched that video, then you have listened carefully. We can zoom in on those areas that has challenges, then we can look at it together. So is there any area of such nature, or should I first of all start by asking, did any one of us watch that video? Did they watch the video?
Yes, I
Yes,
was
I could not
I
finish it because
did,
of some work.
but the topic, like the first topic there, was not the same thing with the one we are going to like do. We are supposed to be in our course material.
What is the name of the course material you are using?
CHM203 Organic Chemistry 2.
Was it the revised version? The revised version has the name that CO3 with March 2021.
No, it doesn't.
It doesn't.
I took this one, the one they gave me in school.
The one they
So
gave you
I
in school, if it is an old one, then you need to migrate on the platform of this revised edition, which is March 2021. Because it's that revised edition that is going to be used to be setting your exam. You know, there's a need to review the courses after 4 years sometime. So if the hard copy of what they have in the hold is what they still have in stock, that's what they will give you. But there may be little changes. That's why I advise you to go to National Open University courseware online. Then you go to Chemistry 200 level. When you search for that CHM203, you will see the latest material there, download it. So that latest material is what I've used to divide this course into the number of weeks of facilitation according to this PowerPoint.
Okay, sir, please, quick question. Like the first topic for this semester, is it molecular architecture, right?
The molecular architecture. Yes.
Okay.
That's
okay.
why we're talking about, is it not the way where we're talking about the interaction, different kind of forces and bonds in organic?
Yes, sir.
Hmm?
Yes, sir.
Or maybe I should share some. Let me check something. Let me share with you now so that we can look at it together to be sure we're on the same page. To be sure we're on the same page. Let me share the online e-learning platform of my own account page with you. Let's see. I hope you can see.
Yes, sir.
So this is my own course page, CHM203 course page. I want to go there.
Okay.
So you see, when you go there, you get to CHM203. This is the course page. These are the announcements that I drop for you. When you click this place, you see the announcement. If you click meet your facilitator, you see the full detail of who I am and how you can contact me by email. I hope you are seeing what I'm sharing.
Yes, sir.
So when you push it
Yes,
up,
sir.
you will see where I put
Yes,
the course material. Can you see CHM203 course material?
Yes, sir.
It's also on your page. Once you go and sign in on your course page and you come to this place, you will see this course material. I've already dropped it there for you. You see, it's March 2021 PDF document.
Yes.
So if you go there, you can click it and download and then go through it.
Okay.
Are you
Okay,
seeing it?
sir.
Are you seeing it?
Yes,
Yes,
sir.
sir. Yes, sir.
Good. So this is the material I'm using for you. And then, of course, if you look at that, there are little modification from what you have before. You see what they call the name is CHM203, which is the course code, and it's organic chemistry 2. Can you see it?
Yes, sir.
Yes.
So you that you may be having organic architectural molecule and all those things may likely be the whole course material that are the hard copy that they still have in stock that they gave to you. So if you have any of those one, you can read it in combination with this one I'm sharing. This one I'm sharing, I've put it on the course page. If you go and open your own course page now and go through the place I showed you, you will see it there for you.
Okay, sir.
Do we get it?
Yes, sir.
So
Yeah.
it's this now I've now pulled out to do. You can see the module 1 is now electronic concepts and stereochemistry. Can we see that?
Yes, sir.
Yes, sir.
You are seeing it. It's made
Yes,
up of
sir.
3
Yes,
units.
sir.
The first unit is factor affecting the structure and physical property. Molecular architecture has to do with when all these factors are considered, then the structures of the compound are known and the property that is related to those structures are known. So there are 3 modules for this course. The first one is electronic concept and stereochemistry. The module 2 is functional group and reactivity in organic chemistry. And the third module is aromatic compounds. And this is the material I have used to prepare your PowerPoint for this course. You can see here now in this content for you to know that it's a modification. If you look at 3.1, you see molecular architecture and factor affecting physical property. So it's just a little change in that nomenclature. It is factor affecting physical property and the structural arrangement of entity that makes molecular architecture to be possible. You know, when you're talking about architectural design, you draft and draw things and join them tooth to tooth, nail to nail, and get a beautiful edifice out of them. So the same way you have the physical structure in building, you can have also the structure in organic compound. That's why the word molecular architecture was used, but there are factors that are governing them. So molecular architecture can be the same thing as physical property of the organic compound and their structure, while the factor affecting them are well stated here in this concept. I hope we get it.
Yes, sir.
So thank you very much. Do we still have any other question?
No, sir.
Okay. So if there is no other question, did anybody watch that video and you have understanding or you have any clarification?
I didn't finish watching the video.
Okay, the few you watched, did you have any question you want to ask me? I want to admonish us, please.
I really didn't understand that electronic concept part.
Okay. Okay, let's look at it. I'm sharing my slides. I don't know whether you have seen it.
We are seeing it, sir.
You are seeing it. Very good. So
Yes, sir.
this is the
Yes.
first topic. We are going to do this today. The topic 2, we'll do it next week, Saturday by 7 p.m. to balance for last week omission. Then the normal Sunday will now start next week Sunday. So I want to deeply appreciate everyone that came on board last week Sunday. I want to deeply appreciate you. So based on that, I will go through this as much as I can. But before next class, which is Saturday, please watch the video for topic 2. And before Sunday, watch the video for topic 3 so that we can come here to solve real-time problems together instead of teaching the whole class again. Okay, so at the end of the topic 1, which is what we are doing today, the learner should be able to, number 1, identify organic molecules using their physical properties. We should be able to expatiate on the melting and the boiling point and the solubility and refractive index, which are the physical properties of compound. They should be able to determine the relationship between molecular structure and their physical property. And we should be able to define and explain the factors that affect the availability of electron in the site of a reaction. That will help us to predict what reaction will go fast, which reaction will go very slow, and which reaction may not even proceed at all. And we should be able to apply this factor to predict some specific things in organic reaction. At least you can use it to predict which organic acid will be stronger, which organic acid will be weaker. So let's try to put a little explanations to this molecular architecture. If the structure of a compound is known, its physical property can be predicted. Because out of the structure, of course, the physical property, if the structures are formed as a regular pattern of arrangement of entities, of course, such compound will have a stable feature, and therefore we have a well-stabilized property. But if something is not arranged, is arranged in an adversarial way, of course, it will also have effect on the physical property. Just like when you are looking at sodium chloride, sodium is interwoven as a plus with the chloride as minus, and chloride as minus interwoven with sodium as plus, and you go in that regular arrangement of pattern. It gives you a beautiful architectural design that confers stability. That's why you expect something like sodium chloride to have a high melting point as a physical property. Whereas when you have some that their molecules are not really in strong ionic forces holding them together, they are not as strong as sodium chloride. So easy melting at a lower temperature will break them down and then cause melting to occur. So we are saying the physical property depends also on the nature of the forces that are holding the unit of that compounds together. And we are going to be looking at that. So in covalent compound, molecules are held together by intermolecular forces. What are these intermolecular forces? In covalent bond, of course, is formed between two entities as a result of sharing. We know that. Ionic bond is formed between two entities as a result of one transferring excess of its electron to another. So in ionic bonding, you have ionic compound form. And because of full transfer and the electrostatic ionic force that holds them together, they will require higher temperature before their solid can melt to liquid, therefore higher melting point. They require a higher temperature before they are liquid and boil to become gases, and that's also higher boiling point. However, for the compounds that are covalently bonded, which means that they share their electron together for both of them to obey their object rule, the bond that holds them together is a weak bond, is a covalent bond. So there are 3 different forces that exist in covalent bond. The first one is dipole-dipole interaction. We have the London force, or we can also call it London dispersion force. And the third one is hydrogen bonding. So little explanation about dipole-dipole interaction. A dipole-dipole interaction means it's not a real bond that exists between them. It's not a real bond that exists between them. It's not a real bond that exists between them. Please, when anybody is joining us, please mute yourself in order not to distract our class. Thank you. Now, when you look at something like sodium, methyl chloride, methyl chloride, the methyl part is having a partial positive charge, and the chloride is having a partial negative charge. If the second molecule of methyl chloride will come in, it will rearrange itself in such a way that the positive will be closely aligned with the negative. So the negative, of course, we always want to attract positive, just like the male will attract the female in a normal setting, not in an abnormal settings that we are having in the world today. So when you see this, the chlorine will align himself to be closer to the methyl of the second one, because they are like partial negative from chlorine, we will be attracting partial positive from the methyl chloride. So when you look at that, it means the head of the dipole moment for the first one is that negative chloride. It will be in alignment with the tail of the second methyl chloride, which is the positive one. So what is connecting them is a dotted line. It's not a real bond between chlorine and methyl group, but yet there's an interaction between them because the chlorine as a partial negative is feeling the effect of the methyl group from the second molecule as a partial positive. The same way the chloride of the second molecule is feeling the effect of methyl of the third. So this kind of things with a dotted line interaction, which is a secondary interaction, is called dipole-dipole interaction. You know, this is a dipole, a positive sigma and a negative sigma. Then the negative sigma will now be interacting with the positive sigma with a dotted line. This is dipole-dipole interaction, DDI. So the dipole results from unequal sharing of electrons. What do I mean by this? If you have methyl group, of course, methyl group has 3 hydrogen with a odd electron because it's not up to 4 hydrogen of methane. Chlorine also has 7 electrons, 6 of them has formed pair. 1, 2, 3, 4, 5, 6. Then the 7th of it need 1 more to become 8. The 1 dot of the methyl need 1 more to become stable. So the methyl will share its own 1 electron with chlorine for chlorine to be happy as 8. And the chlorine will share 1 of its electron with the 1 of the methyl group to be happy with 2. So when that happens, the bond between them is called covalent bond. In this covalent bond, there are different things that can happen. In covalent bond between methyl and chlorine, they are not of the same electronegativity. Chlorine as a group 7 element is more electronegative than methyl group. So even though a pair of electrons is shared between them, if one will not cheat another, the shared pair of electrons should be equidistantly placed between the 2 of them. If it is chlorine and chlorine that share that, you can say yes. They have equal electronegativity, so they will share the distance of electron density equally. But if it is methyl group and chlorine, chlorine is more electronegative than methyl group. So the shared pair of electrons that are supposed to be equally placed between them, chlorine being more electronegative, will pull it towards itself more than the methyl group. And when that happens, you end up forming something in which the electron density of this electron pair is closer here, yet it's still shared between the 2 of them. And in order not to cheat methyl group for what happened there, what happens is that for the electron density of the shared pair to be withdrawn more to the chlorine part, then it makes the methyl group to be like a partial positive, as if it just loaned something out, but not completely. And chlorine that has taken more than it needed, electron density around him will make him to have a partial negative. This is when we have a polar covalent bond. And this polar covalent bond is what is represented in form of a dipole. The tail of that pole is partial positive. The head of that pole is partial negative. But if you look at chlorine gas sharing with chlorine gas, this is not a polar covalent, it's non-polar. because the bonds are equally placed between them. So it will not lead to generating of partial positive and partial negative, because the electronegativity of this chlorine is equal to this chlorine. So both of them are withdrawing the electron density equally. So there will be 50-50, no cheating. So that kind of covalent bond is called non-polar covalent bond. But a bond in which methyl group is less electronegative, and therefore the electron density is pulled more than half of the space where it should be. The guy that have it more will be partially negative. The guy that have it less will be partially positive. So the covalent bond you have between methyl and chlorine is called polar covalent bond. And that's what generated a dipole here. And that's why a dipole for the first one, they begin to interact with the second one. This is methyl chloride. This is methyl chloride. So you see there is a dotted line interaction between the partial negative of the first one, which is chlorine, and the partial positive for the second one, which is methyl group. There's also a secondary interaction between the partial negative of chlorine of the second one and the partial methyl group positive of the third one. This thing called secondary interaction is called the dipole interaction. So it will take a polar covalent bond first to be able to establish the presence of a dipole interactions. The negative pole of one molecule is attracted towards the positive of another nearby the molecule. Example is like methyl chloride. Hydrogen chloride is also another example. If you look at hydrogen, hydrogen has 1 electron in its outermost shell, but it needs 2. Chlorine has 7 electrons in the outermost shell, but it needs 8. So chlorine cannot transfer 1 to hydrogen because it's already having 7, it needs 1. If you have to transfer 1 to hydrogen, it will become 6, better than what it was before. Hydrogen need 1 more to become duplex. Hydrogen cannot transfer its 1. That's why HCl cannot be an ionic bond. But here, hydrogen and chlorine can make an arrangement together and say, let's create a boundary between ourselves. Why me, I will drop my own 1 electron as hydrogen, and you, as chlorine, will drop your 1 electron. So when we want to count for chlorine now, chlorine is having 7 plus 1 that the hydrogen has shared with him, making 8. Chlorine is happy. Hydrogen is having 1 before, but plus 1 that the chlorine is sharing with him, hydrogen becomes 2. A duplex row, making it good. So when you see that is a covalent bond, therefore the 1 pair of electron between carbon, hydrogen, and chlorine is a covalent bond. But normally, if the electronegativity of hydrogen and chlorine are the same, the pair of electrons shared to form this line should be equally placed between the hydrogen and the chlorine. But that's not the case, because hydrogen is far, far less electronegative than the chlorine. So the shared pair of electrons, we have a more affinity towards the chlorine side than towards the hydrogen side. And to compensate hydrogen for that release, then we say it generates a dipole moment, which made hydrogen giving more to the chlorine side, therefore become partial positive. Remember, I did not say full positive, as you have it in sodium. Sodium is a full positive because it has 11 electrons, 2 8s, and the outermost shell is 1. That 1 is making him not to be stable. He already have 8 inner core shells. So 1 outside, he wants to transfer it to somebody that needs it. That is a full plus, and it's ionic bond. But the partial plus is with sigma, is what happens when he cannot transfer it. He will need to share it because he still needs it by himself, and his neighbor's own is needed by him, and his own is also needed by the neighbor. But once the electronegativity are not the same, the more electronegative one, we have higher electron affinity to take this thing to its own side. To take this to its own side. So when we see that, we discover that the negative and the positive partial will become H plus sigma and Cl sigma minus. So that's why HCl can also have secondary interaction between its chlorine and the H of the second HCl, and interaction like that, like that, like that. So the London force is actually in non-polar compound. Of course, carbon and hydrogen has the same, almost the same electronegativity. So the covalent bond that is shared between carbon and hydrogen is always equidistant between the two of them, which makes it to be a very, very important non-polar molecule. So London force occurs in non-polar molecule like methane, like ethane that has carbon, hydrogen, where there is no partial positive or partial negative. An example of that also happened in helium. And this is the explanation, the London force. It's a weak force. Therefore, even though the bond is not very strong, but the accumulation of the atoms make it so. Like, for example, when you look at methane, CH4, it has in a London force. Ethane, C2H6, it has London force. Propane, C3H8, it has London force. Even though it's a weak London force, but by the reason that there is increase of CH2 between each one of them, we make the ethane to have a little higher melting and boiling point than the methane, and propane we have a little higher boiling and melting point than the ethane. Why? Because additional CH2 that you are adding is leading to additional London force. Hydrogen bonding, of course, is a stronger form of a special type of dipole-dipole interaction in which the species that is having interaction with the negative sigma is the hydrogen. You remember in the methyl chloride, it's methyl that is doing that. But anytime the positive, partial positive is purely hydrogen, then you have hydrogen bond. So hydrogen bond occur between hydrogen and a highly electronegative atom, which can either be oxygen or nitrogen or fluorine. If it's the same molecule, if it is the same molecule that has that, then you discover that it is very important to note that hydrogen bond can occur between the molecule of the same elements. You see here that the hydrogen of water is having secondary interaction with the highly electronegative atom of another water, which is oxygen. This is an hydrogen bond. It's not a real line bond, it's a secondary interaction. But because it's within the same molecule, a water molecule interacting with another water molecule, then that is what is called intra. Intra means within. That is intramolecular hydrogen bonding. But if the hydrogen of a compound is interacting with highly electronegative element of another entirely different compound, then it's called intermolecular hydrogen bonding. Yes?
So please, can you like go back and talk about that intra? I didn't get that very well.
Please, let me give every one of us this information. The Zoom link we are using, I don't know why, is trying to tell us that in the next 5 minutes that it will be over. So I will try and find out if it is not a licensed Zoom that we are using, because normally licensed Zoom can take any number of hours. So what I will advise now is that immediately we are logging out, just go back to that link again to continue till we finish the class for today. So I want to go back to the intramolecular. I hope we all get that information right.
Yes, sir.
Intra, when you say intra means within. If you say intracity, it means within the same city. If you say intercity, it means from one city to another. Now, if you have two molecules of water, H2O, and I said hydrogen bonding is a secondary interaction between hydrogen and an highly electronegative element. If you have another water here, H2O, you know this is water, H2O. The first one is also the same thing, water, H2O. Now, the highly electronegative element that can interact with hydrogen to form hydrogen bond are three: oxygen, nitrogen, and fluorine. So if you have this now, there are real line bond between hydrogen and oxygen. But between this oxygen, there is a secondary interaction with the hydrogen. So when the hydrogen is interacting with highly electronegative element of a second molecule of the same compound. You know, this is water, first molecule. This is another water, second molecule. That is called intramolecular hydrogen bonding. Intramolecular hydrogen bonding. However, if we are having, for example, let me talk about another one. For example, let's say you have HF, hydrogen fluoride. It has an electronegative element there, which is fluorine. Fluorine is one of the three elements that can form hydrogen bonding. If there's another thing called water, H2O, you can see the H2O here. Water is H2O, hydrogen fluoride is HF. They are not the same thing. So if the hydrogen of water is having interaction with highly electronegative element of HF, which is fluorine, that is an hydrogen bonding that is called intermolecular hydrogen bonding, because it's between the hydrogen of a molecule called water and the fluorine of another molecule called hydrofluoric acid. Do we get it?
Yes, sir.
Okay. So that's the hydrogen bonding is a special type of dipole-dipole interaction where hydrogen play a key role. And the three highly electronegative elements are the accomplice. This oxygen, the nitrogen, and the fluorine. Anything lesser than these three cannot form hydrogen bonding with hydrogen. Okay. So the melting point, of course, is the temperature at which solid turns to liquid. And it's very important in the sense that it helps us to know the identity of a solid compound. Any solid compound, you can classify or categorize it using the hydrogen bonding. For example, using the melting point. For example, if you look at aspirin and it's a white powder, and somebody gave you something to be an aspirin, and you know, for example, maybe the melting point of aspirin is 135. The first thing you can do carefully at the back of that person is just to take a little of that powder, load it on the melting point machine. If the melting point of it is 135, of course, the online and the literature melting point of aspirin is 135. That's the first thing that removes part of your doubt. But if somebody gives you a white tablet and says it's aspirin, and you went ahead and do the melting point and you are getting 310, or you are getting 60 degrees centigrade, of course, you already know that it cannot be aspirin. That's what we are saying, that physical property helps us to know and to have the adequate information about compound. So the temperature at which solid turns to liquid is called the melting point. So melting point is related to the solid compound.